Unlike the wonderful diversity of elements that make up all of the chemicals that you can learn in chemistry, the constituents of an atom are relatively small in number. You've got the proton, the neutron, and the electron, and that's it. There's not a whole lot of combinations that you can make there. Electrons do virtually all of the chemistry, whereas neutrons and protons just kind of sit there and have mass. To get a sense of scale for how these things fit together, imagine an atom being like a baseball stadium. The electrons are buzzing around in the bleacher seats, and the nucleus, the protons and the neutrons, they're packed together as the baseball on the pitcher's mound. And the individual particles are small, like really small. Like, think of a decimal with 15 zeros before the first number, small, in meters. That's really, really small. But they do have a size. And what's more, protons and neutrons are not fundamental particles. They're composites. As we discussed in the helium shortage episode, protons and neutrons, these nucleons, are basically just tiny bags of nuclear junk. There's all kinds of stuff to be found inside of them. They're a mess, a huge mess. Well, not a huge mess, a really tiny, tiny mess, but a mess nonetheless. The point of today's discussion is to describe what that mess looks like. What's in the mess and where do we start? Let's start with the scaffolding. Coarsely speaking, protons and neutrons are made up of 3 smaller particles. For literary reasons, we call these particles quarks. There are some counting rules for how quarks can fit together, kind of like the valence theory of electronic bonding in chemistry, but these rules are mathematically precise and really well defined. I'll spare you the mathematical nuance, but suffice it to say that quarks are most commonly found in pairs or triplets, never by themselves. Pairs of quarks, those make particles that are unstable, and we'll get to them in a bit. But let's focus on the triplets, those things like protons and neutrons. Now, the quarks that we'll be interested in today have very creative names, like up and down. The proton is made up of 2 up quarks and a down quark, and the neutron is made up of 1 up quark and 2 down quarks. To see how this works, let's do some accounting. The up quark has a charge of 2/3 of the electric charge and a mass of about 2.2 MeV. The down quark has a charge of -1/3 the electric charge and has a mass of about 4.7 MeV. So the proton has a charge of 2/3 plus 2/3 minus 1/3, which is 1 electric charge. The neutron, 2/3 minus 1/3 is 0. Incidentally, the fact that they all add up to whole numbers is a really subtle and interesting point, but for later. So the charges work out. Great, now let's do the masses. The up quark has a mass of 2.2 MeV, and the down quark has a mass of 4.7 MeV. So let's add them together. So for the proton, up, down gives you a total of 9.1 MeV, but the proton mass is 938.3 MeV. Yikes. Okay, well, let's move on to the neutron. So the neutron has 2 downs and an up, so that's 11. MeV. Oof. The neutron mass is 939.5 MeV. Clearly something doesn't add up, but hey, that's okay. Remember, the quarks are just the scaffolding, and the mass of these protons and neutrons sit on top of that scaffolding. So we'll get to that in a bit. The Quark model, as it turns out, explains a lot of really mysterious things about particles like the neutron. You see, the neutron doesn't have an electric charge, but it has a really large magnetic field, and it can interact with magnetic fields pretty strongly, which is kind of mysterious since magnetic fields are usually generated by charges that are spinning or moving in some capacity. But kind of like how the Earth has a magnetic field that's generated by some complicated inner workings inside the Earth, like we discussed in the helium shortage, the neutron's kind of complicated structure of quarks and stuff on top of those quarks is what generates the magnetic field, because we know that it's got some charged particles built inside. But something else. You might recall from our discussion of neutrinos that neutrons decay by turning into a proton and essentially emitting neutrinos and an electron. We can think about this in terms of quarks. So the neutron has 2 down quarks and 1 up quark. The down quark is heavier than the up quark, so essentially one of them decays into the up quark, and that's how you get that. It also explains why protons don't decay, because there's nothing for them to decay into. So finally, let's close this discussion by going back to those pairs. Specifically, let's talk about pions. In our video on cosmogenic muons, you might recall that we talked about cosmic rays coming from outer space and smashing into molecules in the upper atmosphere, and part of the shrapnel of those collisions were pions. There's a bunch of different kinds of pions in the Quark model that are worth discussing. Depending on how you fit them together, you get pi plus, which is a up with an anti-down quark. So that's 2/3 electric charge plus 1/3 electric charge. You might remember at this point that antiparticles carry the opposite charge of their regular particle partners. There's also the pi zero, which is, an up quark with an anti-up quark, or a down quark with an anti-down quark, or some admixture of the two. And pi minus, which is a down quark with an anti-up quark. So once again, minus 1/3, minus 2/3. Pi plus and pi minus have the same mass. They're antiparticle partners. Their mass is about 140 MeV. The pi zeros, they're about 135 MeV, which in both cases, again, are considerably larger than just the sum of the quark masses, although they're about 1/6 the mass of the proton. So for these particles too, these pairs of particles, the quarks are really just the scaffolding for the particle mass. There's a formal, precise theory for how all of this works. And because physicists are nerds, they call it quantum chromodynamics, or QCD. You get it? 3 quarks, red, green, blue, the color wheel, 3. Nerds. But it just goes to show that even understanding this stuff at a professional level still requires some kind of useful memory mnemonic tool set to keep everything in order. Anyway, before QCD was fully understood, it was still known that inside the proton and the neutron, there was a bunch of other junk. There were other particles. And we could tell that by doing experiments. You see, physicists would just slam things like electrons and other particles at a nucleus, at a proton or a neutron, just to see kind of what was inside. It's kind of like how sonar works in a submarine, or frankly, how a flashlight works with the photons bouncing off something and coming back to your eye. You're just detecting whatever it is that you can see. Dick Feynman called them partons because they were part of the nucleus. Again, physicists are nerds. And by doing lots and lots of experiments at different colliders way back in the day, physicists were able to get a precise picture of what the nucleon looked like on the inside. By using higher and higher energies, they were able to probe deeper and deeper into the nucleus, into those protons and neutrons, and what they found was kind of astonishing. So sure, there were those kind of valence quarks, that scaffolding that we talked about earlier, but also inside was all kinds of other stuff, weird stuff, kind of stuff that was inexplicable, and other things like really exotic, bigger quarks that had really no business being there in the first place. And yet they were. Like we've been saying, it's a total mess. One more reasonable picture for the bulk of that mess is to think of it like a goo or a glue. And again, because physicists are nerds, the actual particle that comprises most of that glue has been called the gluon, which is just kind of like a messenger particle for the strong nuclear force. It's a strong glue, and it's why quarks are held together so tightly. In fact, the gluons are kind of mostly just particles that are moving around really quickly. It's a weird mix of binding energy and kind of motion energy that's put together, that's comprised inside the nucleon. And curiously, like almost all of that mass, almost all of the mass of the proton, almost all of the mass of the neutron is comprised of that glue kinetic or binding energy. That residual nuclear force that we talked about that binds protons and neutrons together in the nucleus is kind of like just the boundary effects on the surface of protons and neutrons of this glue. That's why they have to be held together at such a tight range. But anyway, it's fascinating that the proton's mass is almost entirely made up of this kinetic energy, this gluon junk. And it leads to kind of a funny prank that advisors will play on their graduate students during their oral defense. You know, a typical question will go something like, suppose that the mass of all the quarks were to go to 0. What would be the mass of the proton? And the naive sophomoric graduate student will sit there, think about it for a while. Sometimes they'll answer 0, which is exactly the wrong answer. If the up and down quarks had 0 mass, the proton would still have about the same amount of mass because it's all kinetic energy. It's all that crazy glue, all that moving and shaking inside that bag of particles. Springs are a familiar physical model that does a pretty reasonable job of modeling how the gluons keep the quarks stuck together inside of a proton or a neutron. Suppose that the 3 quarks of a proton are all tied together up with springs. When they're really close together, when the springs aren't really extended, the particles are pretty much kind of free and relaxed. But as soon as you start stretching them apart, it takes more and more energy to take them further and further apart until eventually they kind of slam back in on each other. That's more or less how the proton works. In real terms, if you tried to pull one of those quarks out of the proton, you would expend so much energy that quantum mechanically, additional quarks would just pop into existence and the springs would break, creating 2 whole new sets of particles, forming other closed particles like, pions to go with the quarks. This is kind of one way that we can understand what happens when we smash a proton against something else, like an electron or any other particle. Particularly those particles coming in from outer space, those cosmic rays. The proton one of the quarks in the proton kind of overextends itself and new particles are created from all of that energy. Of course, in this model of quarks and gluons as objects with springs, this means that the pion too is 2 quarks bound up with some springy type energy, and that also tends to work out pretty well. Put differently, quarks are confined into the particles like protons, neutrons, or pions by the gluons, by that glue force, that nuclear force, which we model as springs. This confinement can really be thought of as kind of like a condensation, kind of like how a cool glass will cause water vapor to condense into droplets along the side. Or, just rain, that kind of thing. We can think of it almost like a phase transition. The temperature is just simply too low to allow quarks and gluons to freely roam around. As we turn the temperature up, as might have happened, say, in the earliest moments of the universe, those quark-gluon mixtures, those little bags of nuclear particles, can begin to melt. And this is something that we can do at particle experiments. For example, at the Relativistic Heavy Ion Collider in Brookhaven, New York, we take 2 gold atoms and smash them up at really high super relativistic speeds and smash them into each other. And just at the moment of collision, the temperature inside that little collision area is so high that the quarks and gluons kind of melt and form a big soup or plasma before things eventually cool down as the explosion shockwave kind of expands and droplets of that quark and gluon soup kind of freeze out or forms into condensates or protons, neutrons, pions, that kind of thing. Of course, the dynamics of all of this, how you'd model it with precise mathematics, is super complicated and requires like massive amounts of supercomputing time and all kinds of crazy techniques. But hopefully by exposing you to a little bit of the inner workings of the proton and the neutron, I've convinced you that this kind of wild complication is actually super fascinating. And with that, we're done talking about nuclear particles. Thank you, physics friends, for watching. See you next time.